Hey, do you like multiplication?
Maybe.
Uh,
Is that okay?
yeah, it's cool. I like math.
Cool.
Hey guys, let's go over stats lesson 3.7, how to experiment well. And I want you guys to start thinking about a question you have or even an experiment that you would implement. What's our learning targets? After this lesson, you should be able to, learning target number 1, learn how to randomly assign treatments using paper and technology. Learning target number 2, explain the purpose of random assignment. Why do we actually use random assignment? Learning target number 3 are broken into 2. Learning target 3A, identify other sources of variability in your experiment. Remember, this is why is there spread or different numbers. And learning target 3B, explain the benefits of keeping these variables the same for all experimental units. Learning target number 1, if treatments are given to groups that differ greatly when the experiment begins, confounding is likely. Remember the word confounding kind of sounds like confusing. Basically, we're not sure if we want to know if X causes Y. But is it possible that Z is in there that confuses, or Z causes Y, not necessarily X, or is it possibly W? That's what it means to be confounding, or it's confusing. Number 2, the solution to this problem is, what do you think it is? Random assignment. Which means that experimental units are assigned to treatments using a chance process. We have to be very thoughtful of how we assign our experimental units. All right, next one. Previously, we used an acronym, and the acronym we used was DARE, digits. How do you assign them? What do you do about repeats? And when will this end? Okay, so you can use the acronym as long as you are asked to randomly assign treatments. Let's try example 1. In Mr. Tyson's class, 30 students volunteered to participate in an experiment to determine if chewing a mint during a test will increase their test scores on the test. Mr. Tyson will provide mint gum for half the students, while the other half will not chew gum. The same test will be given to every student. Describe how you would randomly assign the gum in each of our treatments. So let's just put out our acronym. We can use that for both, actually. So what do we use that with identical slips of paper? But then what they mean by that is when you cut the piece of paper up, it's actually the same piece of paper. So what are the digits? We're going to use on 15 slips of paper. How many students were there? There were 3. So you can write something like yes, which means they get the mint gum, and on 15 slips of paper, write no. Okay, how do we assign or give this out? Basically, we shuffle in a hat, or somewhere, shuffle in hat, and pass out 2 volunteers. Okay, are there any repeats? There are no repeats in this one. And when will it end? When everyone has a piece of paper. Okay? Let's try now using a random digital random number generator. Okay, so how do we do this with technology? We're going to label each student with a number from 1 to 30. I guess that's the numbers we're using. A number is 1 to 30, and then basically how do we assign it? We're going to generate 15 numbers, or 15 different numbers to assign yes, they get the mint. Yes, they get the mint. Other 15 will get no mint. Okay, so that was assign R. What do we do about repeats? What happens if I get like 0, 5 twice? Well, we need to skip repeats. Basically means get another number. Get another number. And when we have 15 random numbers, because that means the other 15 are the no's. That means that's all 30. Okay. All right, let's go to page 2. Learning target number 2. Explain the purpose of random assignment and experiment. Although random assignment should create groups of experimental units that are roughly equivalent, at the beginning of an experiment, there are other variables that might have an impact on the response variable. The idea that we should use subjects to create roughly equivalent groups is sometimes called replication. Like, can you replicate it with additional, like that previous example, 30 more different students in another class? One reason to keep other variables the same for each subject is to prevent confounding, which we talked about, or confusing. Confounding. The second reason we keep other variables the same is to reduce the variability, the spread of different types of numbers, like it's too far off. In the response variable, make it easier to determine if one treatment is more effective. Than the other. Okay, so let's pretend in this graph, let's do an example of learning target number 2 random assignment, and in some ways we want them to be equivalent. So in example A, students were given, the treatment was a cup of maybe regular Coca-Cola, soda. Let me draw pictures. And Coke has caffeine in it. But pay attention here. The non-caffeine has the same size. So let's just say we give them, 6 ounces. One is caffeine, the other one is non-caffeine, right? What this does is it makes sure that the response that people get, maybe they got a lot of caffeine or a little caffeine. Well, at least it was fair in the beginning. But it wouldn't make sense if I let students choose how much they drink of the caffeine. So let's just be like super exaggerate and make sure we make the point clear. Let's just say I give 6 ounces of caffeine and then 3 ounces of the non-caffeinated, or like Diet Coke, and then we measure their pulse rates. Then this one wouldn't be unfair because you're like, whoa, look at those people with the caffeine, their pulse rates are higher. But remember, now we gave less caffeine. So in some ways, this one's really not fair. I don't know how to say it, but this one is not fair, and this one's more fair because they were equivalent in the beginning. Okay? Let's do an example of this. Can watching fast-paced cartoons reduce the mental functioning of children? 60 4-year-old children were randomly divided into 3 groups. One group was shown, I don't know. So I'm going to do something, and we're going to be doing it next lesson, so I might as well just start. We have 60 4-year-olds, and they're split into 3 different groups. I'm starting to draw a flow chart. One of these was fast-paced. Fast. And then the second one is educational. And then one group was given art supplies. So fast cartoon or TV. The educational is also cartoon or TV. And I'm also going to explicit right here, no TV. So if you think about it, if you divide 60 into 3 groups, that means 20 went into each of these groups by some kind of random sample. All the children spent 9 minutes watching the cartoon or drawing. Afterwards, the 4-year-olds who watched the fast cartoons scored significantly worse than the other 2 groups on 4 different tests that measured brain function. Explain the purpose of random assignment in the context of this experiment. All right. So that's my flow chart. I think a couple things come to mind. The purpose of random assignment is to create different groups or equivalent. Is to create equivalent groups at the beginning of the experiment. Or that's kind of like our purpose or goal. Idea number 2, I'm also thinking, for example, if you let the children choose which activity it is possible, such as one gender, like maybe girls, choose drawing. Like they might gravitate towards one. Well, that was really bad. Now I'm saying drawing. Like one gender might choose, like boys might choose the fast-paced cartoons, or the boys might choose the educational cartoon. And then also something that else could be confounding is gender. So not just preference of shows, but gender. Because girls and boys may we're not saying for certain, differ in the rate of their brain development we wouldn't know any difference in brain function was due to gender or the treatment. Does that make sense? If you guys go back to my little picture, back in, I'm hoping that X causes Y, like what they chose, produces their brain functionality, but Z, the confounding or confusing thing might actually be their gender. That's what I'm trying to point out here. Okay? Let's move on here to page 3. Page 3, learning target number 3. Learning target 3A, identify other sources of variability in an experiment. Good experimental design reduces variability by, this is so big, I'm going to hopefully control or controlling. Controlling the sources of variation. We control sources of variation other than the factors we are testing by making conditions as similar as possible for all treatment groups. Comparison is an important form of control. Every experiment must have at least 2 groups. So the effect of a treatment can be compared with either the effect of a traditional treatment or the effect of no treatment at all. Let's do this next example here. Botox for back pain. Remember, Botox is usually a chemical used for like cosmetic surgeries, like to make your face look nicer. The celebrities, you can look on the internet, like it messes them up sometimes if it goes bad. But anyways, could like that cosmetic chemical help with back pain? Recall the experiment to see if Botox can reduce back pain as described in an alternative example in lesson 3.6. This experiment randomly assigned patients with back pain to receive 200 units of Botox or the placebo treatment. Remember, placebo, my word is that it's a fake. It's not the real thing. Which is saline, which is like salt water, which is like nothing. The decrease in back pain was measured after 8 weeks for each patient. Why was it important to measure each patient 8 weeks after the treatment? If the patients were measured at differing or at different time intervals, the researchers wouldn't know if the type of injection I'm just going to put in here the real or the fake. So the Botox or the placebo, which is like salt water in this case. Was the reason for changes in back pain? So what I'm trying to say is the big idea is that it's a specific time period, right? We're trying to make everything the same. So this one is same time. You wouldn't want to do like the Botox after 4 weeks and the placebo after 8 weeks, and people are like, oh yeah, totally, the placebo, the fake stuff you gave me, or whatever that stuff was. It was awesome because it made my back feel way better, but maybe your body just needed 8 weeks of rest versus the 4 weeks. All right, why is it important to give each patient the same dosage of Botox or saline? If patients, think back to the soda one, were allowed, the caffeine, non-caffeinated one, to choose the dosage, the change in pain would be much more variability. I'm just going to put in there that's spread or different numbers. Then if patients were allowed to choose the doses, a change in pain would be much more variability, like the different types of spread, like I have little pain or a lot of pain than otherwise. Meaning, it would making it difficult to tell if the type of injection made a difference. I remember at school, you guys probably remembered, right before you guys took your state testing like SBAC, you guys came into school and people were passing out like breakfast bars. And can you imagine if someone was passing out a little orange bar versus a really big pink bar? And maybe the students who received the really big pink bar actually did better on the test than those who got the little orange one. Well, you got to make it fair. You got to give it the same amount of whatever it is, okay? All right, let's go on to page 4. Lesson Learning Target 3B. Explain the benefits of keeping these variables the same for all experimental units. Other ways to set up a successful experiment. 1, a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatments. The blocks are not random. You control it as the researcher. In a more specific one, in a randomized block design, the random assignment of experimental units to treatments is carried out separately within each block. And then lastly, another one is called a matched pair. Matched pairs design. Just imagine you are twins. Match pairs design is a common experimental design for comparing two treatments that uses blocks of size 2. In some match pair designs, two very similar experimental units are paired and the two treatments are randomly assigned within each pair. So you give one twin, you give them the small breakfast bar, and you give one the really big one. In other words, each experimental unit receives both treatments in a random order. And then you can switch it the other day. All right, let's do this example here. Example 3b. Major headache. 500 patients were asked if a new medicine would help with headaches. They want to compare it with the old one. Researchers are concerned that other variables might affect the outcome. Draw a flowchart of this experiment. Okay, so it wants us to focus on gender. Okay, so let's have our 500 subjects. Again, we're going to be doing a lot of this next lesson, but I kind of want to introduce it to you early. So they're concerned that genders might affect this new medicine. So what do? We do this one up here. Number 1, we're going to do a block. So let me do the same color. Colors, where are you? There you are. So block. Well, what are our 2 blocks? Well, you can separate. Gender is male and female. Okay, those are our blocks. And then within here, then I'm going to do a simple random sample. And, you know, you can do something like, if this was 200, if it was perfect, you got 250 males, and then 125 get the new headache medicine, and then 125 of them get the old headache medicine. Same thing for the females. So 250 plus 250 gives you the 500 subjects, and the 250 females, we do a random sample, and 125 get the new medicine, and 125 get the old medicine, and we get to figure out, did it work? Okay. This part I want to highlight. The randomized block design. So we got the SRS in this part. So not only did we block by gender, then we randomly did a randomized block design where we're not, it was random who got the new and old medicine. Okay? All right, let's try this one over here. Let's pick a color we haven't used yet. Let's try green. Okay, not black. Black on black. That would not be good. Green, please. Okay, so let's now do this one for race. Okay, let's just say you have 500 subjects. And you can account for all of the major races. So 1, you might have Caucasians. And then you might also have African Americans. And over here you might have Asians. And over here you might have Hispanics. So you split them up. So here's my block. Block is, again, gender. Let's use our color coding. 4 blocks. And so that'd be like 125, hopefully each. Guess the numbers don't really work out. And then for each one of those, you apply the SRS, and then how many would get the new, and some would get the old. Guess it doesn't really work out. Should have done a better number, but 125 divided by 2 is 12.5 plus 50, so 62.5. And let's just use magic. 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 Boom. And this group gets it. Boom. Hopefully you get the idea. And last one. Boom. Does that make sense? Okay. So in the pink, big idea here in this example that we just did is that we were blocking for something that we thought would affect our treatment. In this case, on the left in the blue was gender, and then on the right side we did by race. Okay? All right. Example number 4, I want you to review it all. You read it. I'll have my answers just written out, and then press play when you're done to check your answers for number 4. All right, let's review it all. Multitasking or multiple distractions. Do you think multitasking actually works? Well, researchers in Canada performed an experiment with university students to examine the effects of multitasking on student learning. The 40 participants in the study were asked to attend a lecture and take notes with their laptops. Let's draw it out. Pencil, come to me. That's a color I haven't really used. Let's just use orange. So 40 of these people were split into 2 groups. Half of the participants were assigned to complete other online tasks not related to the lecture during that time. These tasks were meant to imitate student web browsing during classes, right? So you attend class and you're watching Netflix. So let's just say A, multitask. And then group B, they were just simply taking notes with their laptops. They were focused. That's a T. Take notes. At the end of the lecture, all participants took a comprehension test to measure how much they learned from it. The results, students who were assigned to multitask did significantly worse, 11%, than students who were not assigned to multitask. Describe how the researchers could have carried out random assignment. Well, we can use the acronym DARE. DARE, D stands for digits. Use 40 pieces of identical paper and then split them into 2 groups. Write A on 20 of those. Multitask, and you need 20 pieces of paper with the letter B on it, where students were only taking notes only. Well, how do I assign them? The researcher will mix and then pass out the pieces of paper to each volunteer. R means repeats. There are no repeats. And then E, it'll end when everyone gets 1 piece of paper. Basically either A or B. Using a random number generator, label each student with an integer from 1 to 40. So if you have an alphabetical list, person at the top gets 1, and the second person gets 2. And then how do you assign that? Well, you pick 20 unique numbers for group A, and the other 20 get B. So when I say the word unique, you can't repeat. That's why in R, repeat, I say skip repeat. So if you got if 3 comes up multiple times, then you just have to pick another number. And then it ends when everyone has a group. Why was it important that researchers randomly assign treatments to the students? Well, in blue there, the purpose of random assignments is to create roughly equivalent groups at the beginning of the experiment. In orange, if we let the students choose, basically there's no control, better students might pick B, where it's notes only. So they're already kind of geared towards that. I don't want them to pick. I'm picking as a researcher. In green there, because typically more focused students do better on comprehensive tests, we wouldn't know if any differences in scores on the test were from one of the variables, type of students, which is confounding because that's not what I was trying to look for. I was actually just looking if multitasking or not multitasking would affect their scores. Or was it actually the type of note-taking, which is what I really wanted. And then for C, identify one variable that researchers kept the same for all the subjects. Provide 2 reasons why it was important for the researchers to keep this variable the same. Well, I said that the amount of time was the same in the lecture. If one treatment group was allowed to attend the lecture longer, we wouldn't know if the amount of time, or the type of note taking was the cause of difference in scores. That's why I need to control it, that each group had the same amount of time. A second reason why this is important to keep the variables the same is, in blue there, also if researchers let subjects within each group attend lecture for as little or as long as they wanted, the comprehensive test scores would be much more variable, or variability, more spread, the numbers would be more spread out than it would otherwise, making it harder to tell if the type of note-taking made a difference. We wouldn't want to be based on the if the experimental units or the subjects, the students had longer or little time. All right, let's review, make sure we covered all of our learning targets here. We talked about learning randomly assigning using paper and technology. We explained the purpose of a random assignment. We basically want them to be equivalent, same starting point. 3A, we talked about other sources of variability. This is hard because you have to really think about this in real life context. It's not always given to you. And 3B, explain the benefits of keeping these variables the same for all experimental units so that it's not the confounding or different variables, it's the one you were actually testing. So that was lesson 3.7, how to experiment well. See you guys.
Hey, do you like multiplication?
Maybe. Is that okay?
Yeah, it's cool. I like math.
Cool.